right? Then we got kind of into, we started talking about our three processes of attenuation, and we made it through reflection. Anybody remember the two kinds of reflection we talked about? Specular and diffuse, or diffuse also known as backscatter. Okay, specular reflection has to do with hitting a boundary, a smooth boundaries, right? Smooth boundaries that are much larger than the wavelength of the incoming ultrasound. Correct? Smooth boundaries. Okay. One thing we know about reflected sound waves, think of it like a mirror. Specular sound waves, think of it like a mirror. The incident angle is gonna equal the output angle. Okay, so we don't always get reflections back when unless we're hitting the structure perpendicular or a normal incidence, which I hope you guys read up to that point. Then we're gonna get good reflections back. Those reflections are gonna be a lot stronger than the diffuse reflectors, which are gonna kind of come back with weak reflections because that's dealing with a non-smooth surface, a rough surface. Okay. Okay. Diffuse reflection, irregular surface, and will radiate in more than one direction. Guys, if you see my highlighted words, those are what's important to that definition. Okay. Again, you notice how I made it like a flashcard for you, so you want to print that out and kind of study that because you know our quiz may be coming up on Friday when I see you. Hint, hint. Okay. An advantage. Huh? Okay. There you go. So also remember that diffuse reflection, also known as backscatter. Okay. Creates backscatter. Those reflections can still return to the transducer. All right. Okay. Then we started talking about scattering. Remember our two types of scattering, right? Regular scattering and Rayleigh scattering. Rayleigh, however you want to say it. Don't matter to me. Just recognize that word when you see it. All right. Okay. That is scattering. Is random redirection of sound in many directions. Sounds similar to backscatter, huh? Mm-hmm. But backscatter is, we know that backscatter is going to produce a reflection back to the transducer. Okay. That's the major difference. Scattering will not produce a reflection. Okay. All right. Occurs when the boundary is small, equal or less than the wavelength of the incident sound beam. And when we talk about the incident sound beam, guys, that's the sound beam coming out of the transducer. Okay. Incident. That's the primary sound beam. All right. It's described as disorganized and chaotic because it's going in many directions. Lung tissue or air tends to be a scatterer, which is why we can't see the lungs with ultrasound, because as soon as sound hits it, it's going to spread. Remember that analogy I brought up when we were talking about thunder and lightning. Mm-hmm. The reason why you can always see the lightning first before you hear the thunder is because lightning can travel in the vacuum. It can travel through air. Sound needs the medium, so that's why you hear it many seconds later. Okay, similar thing right here. That's why we can't, because it can't penetrate or travel through air. That's why it's just going to scatter, create a lot of scatter. All right.
So what's the medium of thunder?
The medium of thunder? No, sound. You know, sound can travel through air.
Oh, okay.
You know, it just has to be a really low frequency. So if a frequency of less than 1 megahertz, that has the ability to travel through air. Unfortunately, that's not within diagnostic range because we use 2 to 15 megahertz, or really 2 to 17 megahertz, honestly.
Okay. Too high.
So higher frequency sound scatters more than lower frequency. Scattering is directly related to the frequency. All right. Rayleigh scattering, a special form of scattering that occurs when the structure's dimensions are much smaller than the beam's wavelength. So reflection is going to be larger than the beam's wavelength, correct? Much larger than the beam's wavelength. Talking about regular scattering, that's going to be equal to or smaller than the beam's wavelength, and Rayleigh scattering is going to be much smaller than the beam's wavelength. Okay, and I'm just trying to get through there. Redirects sound in all directions. Think about when you drop a pebble into, the pond, how it has that omnidirectional scattering. That's what we're using as the example. Okay, red blood cells interaction with sound creates Rayleigh scattering. Guys, that's going to be on your registry 100%. They're going to ask you, what structure creates Rayleigh scattering in the body?
Red blood cell.
Red blood cell. Bang, bang. What structure creates scatter in the body? Lung tissue. Man, y'all on fire. All right? I want you to know that Rayleigh scattering is proportional to the frequency to the 4th power. Okay? That means if the frequency doubles, radially scattering is going to be 16 times greater.
But they call it really because of the guy that discovered this.
That's my example right there, radially scattering. Omnidirectional means in all directions, guys. All right? Get through that. Get through that. Talked about this already. All right? So now, let's talk about absorption, guys. Absorption is the last of the three processes, right? Reflection, scattering, absorption. Guys, did you know that over 99% of the sound beam is being absorbed? Okay? We're only getting about 1% of reflection, which is why it's so important that we talk about amplification. That's why we have to amplify the sound so much, because most of the sound in the body that we send out, the incident sound beam, is going to be absorbed. Okay? About 99% of it. Okay? So absorption occurs when ultrasonic energy is converted into another form of energy, such as heat. Okay? Because remember, we never lose energy. That's the law of conservation of energy, right? We never lose energy. It's transformed from one form of energy to another. Correct? That's physics like 101 right there. That's physics you learned in high school right there. All right? So, again, like I just said, over 99% of sound is being absorbed in the body. That is the most sizable component of attenuation. Registry. Absorption is the most sizable component of attenuation right there. Like scattering, absorption is also directly related to the frequency. Okay? That means we have a low frequency transducer, it's gonna have less absorption. Okay? And vice versa. Okay? I like the analogy when it comes to that, because Myra really I love her analogy. Okay? So because of absorption, higher frequency waves attenuate more than lower frequency waves. And you guys know that, right? We talked about that a million times. Okay? That's why we use a high frequency when we're doing superficial structures. We use a lower frequency when we're doing deep structures of the abdomen, for example. Okay? Sound traveling in bone undergoes extensive absorption. God, that's so important when we're talking about heat and we're talking about the AIUM guidelines, because bone is going to absorb so much that it's gonna create a lot of heat, and that's when we're talking about our biologic effects. You know, that's why ultrasound is still so young. They're still determining biological effects right now. Okay, that's why you're not allowed to put color on the baby, right? You're not allowed to use Doppler on the baby unless absolutely necessary, because we still don't know how it can affect the fetus. All right. So again, I like this how they have this thing right here. So this is our area of interest right there, the yellow dot. Higher frequency has shorter penetration. That sound is going to be absorbed at a higher rate. Okay, same thing, that sound is also going to be scattered at a higher rate. I just added this today, guys. Okay, but I like how it has the H, higher frequency has shorter penetration. If that helps you, use it. If it doesn't, just know that. Higher frequency it's not going to be able to penetrate the body. It's not going to be able to penetrate the body as effectively. Such as lower frequency transducers, meaning just look at the space between those sound beams. Just pretend these are sound beams. The space between them is a lot less than our lower frequency. Okay, meaning that those events aren't occurring as often. So remember, that's what frequency is. We're talking about events over time. Correct? So these sound beams aren't coming out as often. Okay? I'm sorry, this high frequency. These sound beams are coming out more often. So we can honestly say that this is gonna probably have a higher PRF, correct? We're sending out more pulses per second. I'm never gonna let you guys forget those terms, the parameters. All right? This one right here, you see that is lower frequency because of how deep it's penetrating into this structure right here. That it can actually pick it up on the ultrasound system. Okay? So lower frequency has longer penetration. Bang! This is a classic example. Thank you, Myra, because you're the best for this. Myra helped me come up with an example for us think about track running, you know? Think about sprinters versus distance runners, right? Sprinters, those are a higher frequency, okay? Those legs are moving really, really fast, but they're not gonna be able to maintain that speed over a longer period of time, right? And you can't have a sprinter running at 21 miles an hour for 800 meters, okay? That's our higher frequency. That's why they only run for short distances, okay? Short depths, that's what I'm equating to depths. Where if you have that distance runner, they're gonna be at a slower pace, hitting it, but they're gonna be able to run all day. They're gonna run as long as they want to. Okay? I really like that analogy that she brought to me about sprinters versus distance runners. Sprinters being our high frequency, okay, running at a lot faster speed for shorter distances, and distance runners, marathon runners, running at a lot slower speed, a lower frequency, but they're able to run at a further distance. I really like that. I don't know if that helps you guys. That really helped me. Bang, light bulb. I was like, yeah. Okay. So, absorption. So guys, these are 3 components again. If you guys need me to send this to you and again in a PDF, because I'm always going to be adding, guys. Even though I may have a finalized version, I'm always going to be adding to it because I'm always trying to come up with a way to help explain everything a lot better. Okay? So, if you need me to send it to you, I will. All right? So, we talked about our 3 components. First one being reflection, meaning that the incident sound beam is going to go down and hit a structure. A large structure, whether it be a smooth surface or not. Smooth surface being speculative reflection, a regular structure being diffuse reflection or backscatter. Okay, that sound is going to reflect back. Maybe it may come back to the transducer. It may not.
But it depends on the angle, right?
Definitely depends on the angle and how you're hitting that. Okay, but just remember that we're only getting about 1% or less of the sound beam is being reflected back to the transducer. Okay, a lot of that sound is going to be absorbed or keep transmitting through the body. Okay, so first one will be reflection. Boom, go down, hit the structure. May come back to the transducer. It may not. Okay, next one is going to be scattering. Scattering. These reflections are low intensity. They're not going to even make it back to the transducer. Such as when you looking at the lungs, for example, right? Or we're talking about Rayleigh scattering. What structure is that? Red blood cells. Red blood cells. And the last one would be absorption. Okay, meaning that it's going to keep traveling. Okay, either the sound is going to absorb or it's just going to keep transmitting through the body. Okay, we're good, guys. What are 2 determining factors of attenuation? Length and frequency. And these are our 3 components of attenuation. Okay, reflection, scatter, absorption. The larger of those 3 would be absorption. Okay.
So transmission.
We're coming to transmission. No, transmission would be the sound being absorbed because it's going to keep traveling. Because remember, whenever a sound beam hits a structure, it's going to reflect or it's going to keep going. It's going to keep losing energy. Every boundary of a structure it hits, some of the sound is going to transmit, some of it's going to go back. Okay, we're good there, guys.
So the absorption, the water go through, absorb the acoustic sound? Or
Water?
Yeah.
Water is, it's going to absorb, but it's going to keep transmitting at the same time. Okay? Not to be confused with propagation speed. Attenuation is different than propagation speed, okay? Propagation speed is the speed at which sound travels in the medium.
Yeah.
Okay, when we're talking about transmission, we're talking about impedance. How easily it's able to travel through there, not the speed at which it travels.
Okay.
You guys got it? Law? You good? Too much for you right now? Okay. So, let's do our little attenuation refresher. Okay? Again, attenuation is the process whereby sound is extracted from the wave by absorption, scattering, and reflection. Those are our 3 components. Okay? Total attenuation depends on, Uber said too, the frequency of sound, the distance that the beam travels, and the tissue through which the sound travels. Because we're going to talk about impedance next. And some structures in the body are more resistant to sound traveling than others. Again, like I told you guys, sound's going to travel really great through water, right? Or a fluid. And it's going to travel really great through the bladder. That's why you're going to have that brightness. I know Ms. Shepard talks about this. I was in class with you guys the other day. You have that acoustic enhancement posterior to the bladder because sound is able to travel through there very well. Talking about the lungs, that's going to be a high absorption, high scatter. So sound is not going to be able to travel well through there. So these are the 3 things that total attenuation depends on: frequency, path length, and the tissue through which sound travels. All right? For those reasons, it is difficult to compare the amount of attenuation under different circumstances. Similar to intensity, remember, we couldn't put out one specific number for intensity because intensity varies throughout the time and the space that the sound beam is traveling over. All right? So same thing with attenuation. You can't just pick out one spot and say, oh yeah, it attenuated, yeah, this much. Okay? Because it depends, right? Because what if I'm using a 5 frequency transducer? What if I'm using a 12 frequency? So it won't be the same. All right? The attenuation coefficient is the term used to